Ni hao. Hello. This is the 12th lesson of heat transfer. In this lesson, we will continue discussing steady-state, multidimensional conduction heat transfer problems. In lesson 11, we looked at a method called the finite volume technique for analyzing these types of problems, and showed how to derive the governing equations in the finite volume method. The focus of the 12th lesson is on solving those equations. In the first part of this lesson, we will look at solving the equations in the case of a one-dimensional heat transfer problem. The simplicity offered in the one-dimensional case makes it easier to understand how to solve the equations. After we look at the one-dimensional case, we will move to a multidimensional case. By the end of this lesson, you should be able to recognize that the finite volume method equations for each volume in a numerical mesh form a coupled set of linear algebraic equations. You should also be able to use matrix methods to solve the equations simultaneously in the MATLAB environment for a one-dimensional case. On with the lesson. As a review, we introduced the finite volume method for solving steady-state multidimensional conduction heat transfer problems. The finite volume method is a numerical approach to solving for the heat transfer. Numerical approaches are always approximate. They do not provide an exact solution to the governing equations. However, the approximation can be very, very good. We use numerical approaches because there are so many engineering problems for which there is no analytical exact solution available. In the finite volume method, the big idea is to break up the physical problem into a connected set of small but finite control volumes on which we balance energy. The finite volume method has many advantages compared to other numerical approaches when solving for heat transfer problems. The finite volume method always consists of 3 steps. The first step is to discretize the domain, which means that we must create the numerical mesh to represent the physical problem. The second step is to derive or identify the governing equations for the nodes in the numerical mesh. Steps 1 and 2 were the focus of the previous lesson. In this lesson, we will begin to look at solving the coupled set of algebraic equations using matrix methods. The finite volume method equations form a set of coupled linear algebraic equations. To help you to see this point, we will consider a one-dimensional conduction heat transfer problem rather than a two-dimensional or three-dimensional problem for simplicity. Here is an example problem that we will look at. I will now read the problem statement. A square rod of length L equal 1.1 meter and width W 1 meter is held at 100 degrees C at one end and has the other end exposed to a flow of air that is at a temperature of 0 degrees C and gives rise to convection heat transfer characterized by a coefficient of 10 watt per square meter Kelvin. The rod material has a thermal conductivity of 1 watt per meter Kelvin. The sides of the rod are insulated. What is the rate of heat transfer through the rod, and what is the distribution of temperature? Use a finite volume method with a node spacing of 100 millimeters. Here is a sketch of the problem. It is a square rod of width 1 meter. One end is held at 100 degrees C, and the other end has convection heat transfer the sides of the rod are insulated, such that heat only transfers along the length of the rod. It's thus a one-dimensional problem. And even though we could tackle this problem using a thermal circuit, and we in fact will do that later in the lesson, we are going to tackle this problem with the finite volume method in order to demonstrate that the equations form a set of coupled linear algebraic equations. Here we have established a numerical mesh with a node spacing of 100 millimeters. That's the first step in the finite volume method. Here again is the problem and the numerical mesh. We will use the variable m to count the nodes. Here I have labeled the nodes from 1 to 12. We now need to identify the governing equations for the nodes. Let's begin by looking at an interior node. Here's an example of an interior node. Recall that we always assume that heat transfer is in when we derive the governing equations. We have conduction heat transfer in from the node to the left and the node to the right, QW and QE. We apply the heat transfer energy balance equation. We are considering a steady state problem with no thermal energy generation, and because the convention is to assume all heat transfer is into the control volume, there is no rate of heat transfer out. The heat transfers in are the conduction heat transfer across the left and right faces, denoted QW and QE. Substituting in Fourier's law, and assuming that there is a linear variation of temperature from node to node, results in the following equation. Finally, noting that the area of the west and the east faces are equal, and that the thermal conductivity is equal, and that the node spacing is the same, this equation reduces to the following. The temperature to the west plus the temperature to the east minus 2 times the temperature of the volume of interest. These things must add to be 0. Substituting on our counter variable m, this means that the m-1 node, 3 in this case, plus the m+1, 5 in this case, minus 2 times the mth node, 4 in this case, must be 0. Now we will consider boundary nodes. Let's look at the boundary node at x equals 0. This node is at the known temperature 100 degrees C. So its equation is simply to set it equal to 100 C. T1 is 100 C. On the right-hand side, at x equal L, we have the 12th node. Let's look at the equation for this node. First, we assume all heat transfer is in. Heat transfer occurs across the left face by conduction and across the right face by convection. We apply the heat transfer energy balance equation. We are analyzing a steady state problem with no thermal energy generation, and we always assume that all heat transfer is in when deriving the governing finite volume method equations. We thus have the following. The conduction heat transfer plus the convection heat transfer must add to 0. Substituting Fourier's law for the conduction heat transfer and Newton's law of cooling for the convection heat transfer gives the following. Again, we note that the areas are the same across the left and the right faces. Both are W times W. Now we simplify the equation by multiplying by delta x over k. Finally, we note that this applies the west volume is the 11th, T11, and the P volume is the 12th. We've simply made those substitutions here to give our equation that governs the heat transfer on the boundary node at x equal L. These are the 3 forms of equations that govern the heat transfer in this numerical mesh. We have 12 nodes and thus 12 finite volume method equations. The equations are coupled because temperatures from more than one node show up in each equation. Let's look at each equation one by one now. For the first node, the temperature is simply set equal to the boundary temperature, since this boundary condition is known temperature. In the second node, we apply the interior node governing equation. The temperature of the second node depends on both the temperature of the first node, which is known, and the temperature of the third node, which is an unknown. In volume 3, or node 3, the temperature of the third node depends on the temperature of node 2 and of node 4. The temperature of node 4 depends on the temperature of node 3 and node 5, and so forth and so on. Hence, the equations are all coupled together. At the 12th node, where we have the convection boundary condition, the temperature of the 12th node depends on the temperature of the 11th node. Here I have moved the known term with T infinity to the left-hand side. These 12 equations form a set of 12 coupled linear algebraic equations. Let's now look at how we can solve these equations simultaneously for all of the unknown temperatures, T2, T3, T4, all the way down to T12. To do so, we will note that for the particular conditions in this problem, the term, the convection heat transfer coefficient times the grid spacing divided by the thermal conductivity, is equal to 1, because we had a convection heat transfer coefficient of 10 watt per square meter Kelvin, node spacing of 100 millimeters, and a thermal conductivity of 1. Also, note that that term times T infinity, which is the left-hand side of the node 12 equation, is equal to 0, since T infinity is equal to 0 in this case. These 12 equations can be represented in matrix form as follows. There are 2 vectors and 1 matrix. We have the constants matrix, which is the left-hand side of the equations. We have the so-called coefficient matrix, and we have the variable matrix, which contains the 12 unknown temperatures, or in this case, T1 is known. Symbolically, this matrix representation can be represented as follows. The constant vector is equal to the coefficient matrix times the unknown temperature vector. To solve the equations, we can use matrix methods. We need to invert the coefficient matrix and then multiply the inverted coefficients matrix with the constants vector. It is easiest to complete this step with the aid of a computer. I recommend using MATLAB. The command in MATLAB is the backwards slash. If T represents the vector of unknown nodal temperatures, A represents the coefficient matrix, and C represents the vector of constants in the MATLAB environment, then the command to solve for the unknown temperatures is as follows. T is A \C. The result of this computation is stored in the vector T. The use of the backslash enables MATLAB to find the computationally most efficient method of inverting the matrix and solving for the unknown temperatures. This command will perform the calculations and store the result for the nodal temperatures in T. Since the problem is one-dimensional, we can compare the result from the finite volume method analysis with that from a thermal circuit analysis. This particular problem is represented by a thermal circuit with 2 elements, one representing the conduction through the rod, and one representing the convection out of the end. The known base temperature is denoted by TB. To solve this thermal circuit, we first find the rate of heat transfer through the circuit. For the given conditions, this is 83.33 watts. Then we can compute the unknown temperature, surface temperature at the end of the rod. For the given conditions, it is 8.3 degrees C. We thus expect the finite volume method to provide a linear change in temperature from the base temperature of 100 C to 8.3 C in the solid rod. Let's look and see if that's the result that we obtain when using the matrix inversion method in MATLAB. I will now show you how to do the matrix inversion method in a code. Here is a code that I have set up to perform the matrix inversion method. I provide the inputs, and then the most important parts is I create the constants vector and the coefficient matrix. There are a number of ways in which you can do this. The approach that I have adopted here is only one possibility. For the constants vector, I first create a vector of zeros. This is the result of that line 20. Then I replace the first row and the last row with the appropriate values. The first row becomes 100, and the last row stays as 0. Now we have a 100 and many zeros, like we should. Now I create the coefficient matrix. The coefficient matrix is 12 by 12. It contains mostly -2s on the main diagonal, 1s on the upper diagonal, and 1s on the lower diagonal, except for row 1, where the temperature is known. If you compare this result with the coefficient matrix that we showed in the previous slide, you will see this is the right definition. One could create this by hand and then import this into MATLAB. I use the commands diag to create the diagonal components and add them. The main diagonal, the upper diagonal, the lower diagonal, and add them together. Then I adjust the first row and the last row for the appropriate boundary condition equation. This code will be made available to you. Then you can see the line that solves for the temperatures. On this slide, I have created a graph of the finite volume method solution along with the analytical solution from the thermal circuit. Note that the finite method solution agrees with the analytical solution exactly as it should. The temperature for the finite volume points are denoted with the black circles. There are 12 corresponding to the 12 nodes in the mesh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. The first node is at 100 C, corresponding with the boundary condition, and the second node is at 8.3 degrees C, corresponding with the boundary condition calculated from the thermal circuit analysis. Of course, energy continues to transfer into the fluid at 0 degrees C. Hopefully you have seen in this lesson that the governing finite volume method equations form a set of coupled linear algebraic equations. These equations are most easily solved using matrix methods and can be done in the MATLAB environment or any other computer environment that you are aware of for solving coupled sets of linear algebraic equations. In this video, I demonstrated how to solve a coupled set of linear algebraic equations using the matrix inversion method in the MATLAB environment. In the next lesson, we will look at a two-dimensional case.